So in this session, we're going to look a little bit further at the detailing of cross-laminated timber, and we're going to look at specific detail on this dRMM project, which Ollie mentioned. Okay, but first of all, what we're going to do is go in, have a bit of a look at cross-laminated timber. Now, one of the larger importers of CLT into the UK is KLH. So if you want to go and have a look on the KLH website, there's a huge amount of information on there. And just want to have a look at an example project here, which is an academy in Norwich. What I like about the KLH website is they give you a lot of the stats for the projects in terms of CO2. They sometimes give you the stats in terms of the carbon emissions in transport. This one's not doing it, but what they are saying here is total stored sequestered carbon 760 tons for this project. What they normally do is give you on the website, they give you the breakdown. So they'll give you the breakdown of how much CO2 has been sequestered during the project, how much CO2 was expended or emitted in shipping the panels from Austria to the UK, and then in putting them on the back of a lorry and transporting them to Norwich. So they give you all of those stats, and they're fairly sort of open about it, so you can normally then see the kind of environmental benefits of using CLT in these projects. So that's the KLH website. There is a Scottish company who are hopefully going to be producing our first UK CLT very, very soon. So at the moment, all of our CLT, all of this stuff, you have to import it from Austria. But hopefully, if this Scottish company gets it working commercially, we could be having some homegrown, home-built CLT, which would be fantastic. Okay, let's have a look at their catalogue. They have a very informative catalogue, full of lots of details. So if you are thinking about using CLT in a project, download this catalogue. Bearing in mind, you're not structural engineers here, so some of these details are about how you make these connections structurally work. But the great thing you'll see about the details, typically, is just the simplicity. And as Ollie mentioned, because it's a flat panel product, you end up with a flat surface you can screw into it. Which, if you compare that with, say, for example, a steel construction, where you have to then fire protect all your steel work has cross bracing, you have to interface that with other materials. This is a much simpler product to detail. So here's some simple details at the base, how you fix the CLT to the concrete. I'm not going to talk through all of these. You can have a look at them yourself. But some more base details, and you can see, as Ollie mentioned, some of the different kinds of fixing plates that you use, and these very, very substantial screws, which they drive in. They drive it in with an impact driver. So a lot of them, it's amazing actually that you don't need to pre-drill them. You just get a powerful impact driver, and those big long screws, you just drive them into the product, and they cut their own hole as they drill in. Really fantastic. So there's some corner details, wall to wall, and these are the steel fixing cleats. If you really don't want to see those, then your engineer can design those so that they're hidden and integrated into the timber panel. But normally, like here, it doesn't matter because you're going to be laying a floor on top of that to hide it. But certainly you can design those out. Just a few angled connections. I mean, you can see how simple it is here. They simply cut the CLT to the right angle, and then they put some huge screws through it. Very straightforward. Some other type of connections there. different ways of joining panels, different angles, using the screws at multiple angles. What's that? That's a sealing joint. Just putting in these little cover pieces sometimes to conceal the joint. Connecting it to a beam, connecting it to a steel. Pretty straightforward. Embedding a steel into the depth of the panel. Different types of slab connections. I mean, as I say, a lot of this kind of detail about how you actually screw it together, you don't need to worry about that. The engineers would take control of that. Okay. Some of the details in terms of air tightness. The product is quite airtight, but you put a sealing layer in at the connection just to make an airtight join. More of the same. Electrical installations, so the different ways that you can drill or you can recess conduit. You can make channels in the wall if you want to hide electric cables. I mean, a lot of people, if they want to see this product, see the face, they'll often just fix the electric cables in galvanized conduit, because you could argue why kind of degrade this material by drilling it and recessing it, which means that at the end of this building's lifespan, this timber panel has got all these recesses. Why not just fix it on the surface with galvanized conduit, which most architects are quite happy with that. Looks kind of industrial, looks good, looks fine. Gives you great flexibility in terms of changing your wiring at a later date, compared to all of this. You'd have to break into this wall if we wanted to change the wiring here. What's this? Slots, openings. Yeah, so that's that KLH manual. So download that. If you want to use this material, just download that and have a look at that. Okay, so we'll go into this window detail now and we'll have a bit of a look at drawing this. Okay. So as always, we'll start by drawing our structure. So let's draw a wall like that, which I guess is about 100 mil. Yeah, it's about 100 mil thick. And we'll draw, as per last week, we'll draw at 1 to 5, which I think is just a good scale to start with. In fact, no, I think we'll draw at 1 to 5. So I'm going to start by drawing our CLT wall panel. Okay. And I'm drawing the corners have been chamfered off on this detail. I've got the detail here. I'm using the detail again. Okay. So they've chamfered the corners off. You don't have to, but it makes probably makes a better detail. And if you look at the sample here, if you don't chamfer the corners off, you could end up with kind of irregular parts. You could end up with sharp bits. So quite a good idea here, just to 45-degree chamfer off the CLT. And this is a vertical section through one of those windows. So it's one of those windows which, if I draw it in elevation, it was one of these curvy ones that looks something like that in elevation, but when we draw a section through it, we're just seeing the straight edges of it. Okay, so there's our CLT, and what we'll do is we'll just put a sort of hatch in there, just to make that look like CLT. Okay. Has anyone ever used CLT in one of their design projects before? Yeah? You have, yeah? I mean, I would certainly encourage you this year, when you're starting to think about your project, think about your building and your structure, as Ollie said, if you can, it's kind of the new concrete. If you can use CLT, the environmental benefits are massive. So, I would say it should be your first option for a building, or timber frame. Have a look, see if you feel it's appropriate. If it's not, then maybe you need to use some other materials. But apparently there's a housing scheme in Australia that's been built now, which is 18 stories high, made of CLT. So structurally it is incredibly versatile, and you will, for your purposes this year, you will have a much easier time justifying your material choice if you opt for something like CLT, compared to if you say, well, it's a steel frame, and then you may have questions thrown at you. Well, why is it a steel frame? That's what a contractor might like to use because it's simple for them and it might be cheap. But why are you, as a student of architecture, why is your first choice a steel frame? We did have some steel frames last year where it was quite clear they hadn't really thought about it and they just sort of defaulted to a steel frame. But the embodied energy is huge. Okay, so here's go back to our window, and this is the window with the Cox Dome. So if I just go back to the picture there. So this is what we're looking for. This is what's called a Cox Dome. So it's a proprietary plastic product which you normally use on a roof to make a roof light. And that's how you can achieve this curved appearance. And I think what dRMM are doing, which is very clever here, is on a project like this, you could never afford to buy a bespoke piece of curved glass, doubly curved glass. It would cost a fortune. You couldn't do it. But what they're doing is they found this really kind of attractive, off-the-shelf, cheap product. And they're thinking, well, if we use it in a different way, we get a really interesting appearance for something which is very cheap. Okay. So what I'm going to do now is I'm going to draw that Cox Dome in place. And it sits back here. Okay, so there's that. There's that. Spot the mistake there. Okay, so that's the Cox Dome, and what they've got behind that is the double glazed unit, which is working thermally and is working in terms of acoustics. So I'm going to draw it, and I'm going to I'll ask you in a minute if anybody can spot the inherent problem with this detail. I meant to ask Ollie and I forgot to ask him again. So this is a double glazed unit. Okay, zoom in a bit now. So that's the double glazing. And you notice that what they've done is this double glazed unit here is not sitting in a frame. So they've actually just bought a sealed unit of glass, which is kind of risky in itself because that means people are carrying that around site. If you drop it, you break it. Okay, that's like that, and that now needs to be held in place. And what they've done is simply use some timber pieces. So they've got a timber bearer here, and they've got a timber bearer here. So just a plank of timber, basically. And because this is timber, very easy to fix. We can just put some screws through that. Screw that through into that CLT. Okay. And then what they've done to hold this whole kind of arrangement together, they've just actually put a sheet of plywood here, which is kind of in keeping with the whole detailing approach. That, you know, they didn't want to introduce a piece of a steel angle when you could use simple bits of plywood and timber. So some plywood there. Okay, and again that can be screwed through. And that's now clamping that Cox Dome in place. Now, what you don't want is all of these different materials, plywood, plastic, glass, all sort of pushing up against each other, because they're going to rub against each other, and if you had any variations in thermal expansion, you could get things cracking and breaking each other. So all they're doing is using neoprene strips, which are kind of compressible strips, basically rubber strips, rubber blocks, which are put to clamp in between everything that's clamped together, and that allows things to move about. Also, it gives you an airtight seal. So if you look where my pen is there, by putting that neoprene strip in between the glass and the timber, CLT, you make an airtight seal, because you don't want, obviously you don't want leaky windows. Okay. So that's the kind of, pretty much that's the window done. The interior face is just left as the CLT panel, and as Ollie said, they put an intumescent coating on it, a clear coating, which gives it a Class O classification in terms of spread of surface flame. Okay, because in all public buildings and most buildings, you've got two aspects of fire protection. One is about whether a fire will burn through this material. So if there's a fire started in this room, would it spread into the room next door? But the other issue is about surface spread of flame. And you have to make sure that the materials you use don't spread flame across their surface. And an untreated piece of cross-laminated timber, it would allow flame to spread across its surface. So once you put one of these clear coatings on, it will stop it doing that. And you can get some quite kind of eco coatings now, which don't smell, and you know, they haven't got a whole load of nasty chemicals in them. Okay, so I'll press on with this detail, and then I want you to see if you can start to see what there is an inherent problem with this detail. Okay, and I'll ask you in a few minutes what you think it might be. Right, what they've got on the outside of this building is a profiled aluminium sheet. So this, it looks a bit like timber planks, but it's actually an aluminium profile. Okay, so it's a powder coated sheet of aluminium which is pressed into shape. Okay, so let's just draw that. So that's kind of out here. Here, and it's the same underneath. So that's the outside cladding, this kind of profiled sheet. And obviously we need to do something to seal around this window opening. Okay, so first thing is they need to make sure that any rain which happens to get into this zone, they need to make sure that they're throwing that out of the building. And what they've done here, which is pretty simple, is again they've fixed another piece of timber onto here. And all they've done is flashed over the top a damp-proof membrane. So a kind of fairly thick piece of plastic, basically. Okay, so that's flashed over the top. You can get sticky back, you can get double-sided, very thick, sticky rolls of tape, which you can actually use to stick this stuff together. So if you imagine your normal double-sided tape, peel the layers off, you stick two surfaces together. Imagine that, but imagine it like 5 millimeters thick, and quite kind of rubbery stuff, so that when you then, if you want to stick it to say timber, because it's thick and compressible, it will squash and fill all those gaps, and it'll stick like nobody's business. Okay, this is proper sticky stuff. Okay. And that's often what they will use here is just a bit of sticky back tape to stick that down. Because the thing to bear in mind is we're not expecting rain to be pouring down this cavity. We're just being careful that if any moisture gets in there, we want it to drain out. We don't want it to sit on the top of our window here. Okay, so we've got that. Then they've got a really pathetic amount of insulation. Looks really thin, but anyway, I'll draw what they've got. They are showing a 50mm, I suspect, probably a 50mm closed cell foil-faced insulation in here. I mean, 50mm will be adequate, but you'd normally try and get a bit more than that in, to be honest. But it's difficult when you're working with a contractor and you say to the contractor, I'd like to have 100mm of insulation in, and they say, well, how much do you need for building regs? You say 50. So what do I want 100mm for? So you have to be quite strategic about how you try and argue that. Right, I've then got the same insulation down at the bottom. Like that. And what we've got is we've got aluminium cladding rails which are holding this cladding in place. So these are quite lightweight aluminium extrusions. Like this. And these have various holes and slots pre-drilled in them, and all you're basically going to do is these will have a proprietary bracket something like this. Which allows you to periodically connect those aluminium vertical rails back to the CLT and just hold it all in place. Okay, so there's our kind of wall almost finished. They've got a trim here, which is an aluminium pressing just to neaten up that edge, and then to hide all of this construction build-up under here, they've got another aluminium trim, which just sits in there, and that can just be screwed in place. Okay. And then at the bottom, got a kind of similar detail, but the aluminium flashing is now a windowsill, and so that's fixed with a slight angle onto it. I haven't drawn that quite right there. Run out of space there, to be honest. That sits on a timber bearer here, just to hold it in place. And then all they're relying on is there is a bit of mastic sealant here at the back and here. But the idea is that most of your rain will be hitting that sill and will be draining off. Okay, so you're not expecting a lot of rain to get into here or here. Okay, so almost done on that. I'll just go back to the picture. So that's the view looking up. So you can see this, you've got this aluminium trim all the way around. It's got some screws fixing it in place. There's some screws at the back there, just holding the Cox Dome in place as well. So that's the pretty much the finished detail. The other thing they've got an insect mesh. You want it with all cavity wall constructions like this. You need to make sure you don't allow ants and bees and wasps to get inside your construction, because ants and bees and wasps will love to set up home inside here. It's a lovely place for them. So what they've got here is, it's probably very difficult for you to see it because I've drawn it so small. They've just put an insect mesh over the top here and underneath here, just to try and keep those insects out. I mean, you find these insect meshes they're very delicate, and they probably won't last forever. But at least there's a kind of an idea about keeping the insects out. Then we've got another one of those aluminium bearers down here. Which is fixed back to this aluminium cladding rail with some kind of bolt. Okay, so that's the kind of basic detail. Anyone suggest a potential problem with this detail? Yep. Yeah. 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 Yeah, you're right. It wasn't one I was looking for, but you're right. Yeah. I mean, maybe what you could do, given the amount of space in here, you could pack a bit in. I mean, you could stuff a bit of insulation in there. And I mean, looking at the cavity size, yeah, I think you could even put a bit of insulation, maybe like that. Yeah. then the same applies at the bottom. Yeah, so it wasn't what I was looking for, but you're dead right. Yeah. Anyone else see a? Yeah. 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 Again, it's not what I was looking for, but you're dead right. I'll come back to it. But yeah, because this double glazed unit is a factory sealed unit. So yeah, you buy that from the factory, all sealed up in a clean environment. You don't expect anything to get in there. It shouldn't leak. But this cavity in the glazing between the Cox Dome and the glass is something that you're asking builders to kind of put together on site. And yeah, the potential for that join there and that join there to leak, and you get condensation in here, is quite significant. Yeah. Yeah. Richard, you got another one?
I imagine it's quite dark inside, with that kind of depth of wall and then the glazing and that as well.
Yeah. Yeah. Absolutely. I mean, looking at some of those pictures, it looked like they were relying on a lot of electric lights. Yeah. Yeah. You can't that's deliberate because it's an acoustically sealed space, so you can't. That's not the problem. Anyone see the problem I'm thinking of? Yeah.
Could the cavity between the back of the curved window, the area that be heated up or controlled, so the outside shell, curved shell can change the shape, so the water actually come between the aluminum
Here. Yeah. Possibly. Yeah. I must admit, I haven't drawn that entirely correctly at the bottom, but I think you are right that yeah, that is a weak point, because if you think on a more conventional window, if I draw a more conventional window over here, and I'm drawing this at twice the scale, so I'm drawing this at 1 to 2, thereabouts. Just draw this quite quickly. So yeah, on a more conventional window, everything's about dripping rain off. So rain runs down the glass, drips off onto the frame, drips off onto the subframe. That should have a better angle on it. Drips off the subframe, drips onto your sill, drains down the sill, and drips off your sill. So you're relying on water just to drip off. Yeah. Whereas here, even though I haven't drawn it quite properly, you are relying on that mastic perhaps. And I think as Shin says, if anything moves, you could have a weak point. Yeah? Yeah. Anything else? I mean, they're great. I've got one more, but yeah.
The windows get damaged.
Yeah. Yeah, that's the one I was thinking about. Yeah. Yeah, the only way to reglaze would be to take the wall apart, which there are two reasons why that would be considered bad. One is because it's a school, and school children do break windows sometimes, but also double glazed units can just shatter of their own accord due to imperfections in the glass. So you do get instances on site where the odd double glazed sheet will blow, and often it's the inner sheet will just explode and shatter. And you go on site and say, "Who's done that?" And they say, "Oh, well, it's just blown because there's an imperfection in the glass. It's got on site, the temperature's different, and shattered." So yeah, can you imagine if you got the call from site 6 months on saying that glass has blown, we didn't break it, it's blown, can you come and repair it? And you've got to disassemble the entire wall to get into it. So yeah, serious fundamental problem there. Yeah. I mean, I like the approach. I think it looks great. I think what they've achieved is really interesting. I suppose maybe the thing would be to go back and I'll ask Ollie, has it performed? Because I suppose on the one hand, I'll just go back to this. This is a more traditional, tried and tested approach. We know this will work. But then I suppose you could say, but do you want all your buildings to always look like this? Or would you rather have some buildings where they try something and maybe they find over time this actually works okay? So it's risky. It's risky. I always ask myself, if it was my house and it was my money, would I do that? Maybe not. Maybe not. Okay, we'll call it there. It's far too noisy from next door. So, yeah, that's that. All right. See you next week. Thank you.